In this video, we're going to do some extra examples using the substitution method for indefinite integrals. So let's jump right in. So the first ones are hopefully a bit easier than the ones we're going to see later. So I wanted the indefinite integral of 2 times the square root of 2x plus 1. So what I'm going to do is I'm going to let my u be the inside of the square root, so 2x plus 1. And then my du is the derivative of this, which is 2 times dx. And I actually see that I have a 2 dx there. So if I rewrite this, it's the square root of 2x plus 1 times 2 dx. So I see that this part is going to be my u, and the 2 dx is actually du. So I can simplify, I can switch to u's by saying this is square root of u times du. Okay, which means that it's u to the 1/2 du. And now I can use the power rule, or the reverse power rule. So I add 1 to the exponent. So that's 3 over 2, and then it's going to be 1 over 3 over 2, which is the same as 2/3. And now that I've done the integral, I lose my integral sign. Okay, so that's this and the du. And I switch it with a plus c. Okay, so that's my constant of integration. And now I want my answer in x's, so I switch back to x's. So I'm going to have 2/3 times 2x plus 1 to the power 3 over 2 plus c. And this is my family of antiderivatives. So that's my indefinite integral. And if you take the derivative of that, you should get 2 square root of 2x plus 1. So let's try another one. Okay, so here I see that I have something to the power 10 times some other bit. Okay, so I'm going to start by let's let u be that inner bit. Okay, so 3x squared minus 4x. Okay, what happens when I do that? So that means that du is going to be the derivative of u. So that's 6x minus 4 times dx. Okay, and again, I see that I actually have this entire thing in my integral. Okay, so that means that this part is going to be my u, and this whole thing here is in fact my du. So when I go to u's, my integral becomes just u to the 10 times du. So I can take the antiderivative using the power rule. So that's 1 over 11 u to the 11 plus my constant of integration, so plus my c. And now I switch back to x's. So this is 1 over 11, 3x squared minus 4x to the power 11 plus c. And again, if you take the derivative of this, you should get the integrand that we started with. Okay, let's try another one. So here I want the indefinite integral of x times e to the 3x squared. So this one's a little bit harder. Okay, but I'm going to let my u be the exponent of my exponential function. So that means that du is the derivative 6x times dx. So here's the first time where I don't actually have 6x dx in my integral. I only have x dx. So what I'm going to do is replace. I'm going to solve this equation for x dx. So I'm going to divide both sides by 6. Oops. Okay, so 1 over 6 du is actually x dx. Okay, now if I rewrite the integral, so it's e to the 3x squared times x dx. Okay, so the 3x squared, that's my u. And my x dx, that's 1 over 6 du. Okay, so then my integral becomes e to the u times 1 over 6 du. And 1 over 6 is a constant, so I can pull it right out of the integral. And so now I want the indefinite integral of e to the u du. So I want a function that has derivative e to the u. Well, that's actually just e to the u. Okay, so plus c. And then now I want to switch back to x's. So this is 1 over 6 e to the 3x squared plus c. So that is my antiderivative. So for each of these, I didn't know the integral right away. So that's why I wanted to try substitution. And the way that I picked my substitution was to look for a function that's inside of some other function, or the exponent of some other function, that's the same as being inside, where its derivative is there, okay, or kind of there. So off by a constant, but there. Okay, so let's try some more. These ones are a little bit harder. So for this one, I have the integral of e to the 3x divided by e to the 3x plus 1. So here it's a little bit harder to pick my substitution. Okay, I don't know what has derivative this immediately, so I think I want to use substitution. So if I picked e to the 3x or just 3x, okay, I can replace this, or I can have e to the u here and e to the u down here, but it's going to be difficult to do anything with this because it's in the denominator. So a good choice, if you have a fraction and no sort of powers, okay, a good choice is let's just try to use the denominator. So if u is e to the 3x plus 1, then du is the derivative of this. So that's e to the 3x times the derivative of the exponent, which is 3, times dx. So I think that this looks promising. And the reason is because I could rewrite this as 1 over e to the 3x plus 1 times e to the 3x dx. And now I can see this part is kind of here, right? So if I move that 3 over, so I have 1/3 du is going to be equal to e to the 3x dx. And now I know how to substitute. Okay, so this part, this is my u, and e to the 3x dx, that is going to be 1/3 du. So I think my integral is going to get easier now. Okay, so it's going to be 1 over u times 1/3 du. Okay, the 1/3 can come out because it's a constant. So it's 1 over u du, or u to the minus 1 if you prefer. Okay, so it is a power of u, but this is the one power where we can't use the power rule. So we want to remember what has derivative 1 over u, and it's actually ln absolute value u plus our constant. So now when I plug in my x's back in, I'm going to have 1/3 ln e to the 3x plus 1 in absolute values plus c. I don't actually need the absolute values here because e to the 3x plus 1 is always a positive number. Okay, but we can keep them. Doesn't hurt. So this would be my answer here. Okay, let's try another one. So again, this one is hard to pick my my substitution. So I'm going to rewrite it. Okay, so there's 2 times 1 over ln x times 1 over x dx. Okay, so I just split all of these bits into their parts. And now I can kind of see, okay, 1 over x, this is the derivative of ln x. So if I use u as ln x, then this is going to be part of du. Okay, that seems promising. Okay, so let's let u just be ln x. Okay, then du is going to be the derivative of that, so 1 over x dx. And so I actually have these pieces. Okay, so this ln x, that's my u, and 1 over x dx, that's just du. So this integral, I can pull out the 2, but it becomes 1 over u du. Okay, that's what we had before. So this is 2 ln absolute value u plus c. And you're not going to like the look of this, but it's fine. So it's 2 ln of absolute value ln x. So it's ln of a ln, but that's just a number, okay? You're going to get a number here for each x. For each x bigger than 0, I should say. But okay, so that is my indefinite integral here. Okay, so it looks worse than it is. Now, what about some trig ones? So here, I have the integral of cosine x to the power 7 times sine x. So remember that this is our lazy way of writing cos x to the power 7 times sine x dx. Okay, so just like we did before, cos of x is inside some other function. So that seems like it might be a good thing for u. Okay, so let's let cos u be cos of x. Then du is the derivative of cosine x, which is negative sine x times dx. And I actually see sine dx. So sine x dx. If I move the negative over, negative du is exactly sine x times dx. So that means this part is my u, and sine x dx is going to be negative du. Okay, so that means my integral becomes u to the 7 times negative du. So I can pull out the negative, and now I can use the power rule. So it's negative 1 over 8 u to the 8 plus my constant. And that's going to be, if I plug back in the cosine, negative 1 over 8 cosine to the power 8x plus c. Okay, so that is my indefinite integral here, or my family of antiderivatives. And again, you can check your work by taking the derivative of this. You should get this integrand here. Okay, let's try another one. Now this one definitely doesn't seem obvious what our substitution should be. I mean, we could use 2x, but then we're still not going to know the antiderivative for tan x or tan u. So what I'm going to do is rewrite this. So I know that tan of x, or tan of 2x, is going to be sine of 2x over cos of 2x. Now if I write this even further, it's 1 over cosine of 2x times sine of 2x dx. Okay, so again, I have cosine in the denominator, and the denominator is something that I know I can pick, that can be useful. And the derivative of this is something like this. Okay, so that seems promising. So let's let u be cosine of 2x. So then du is, I need to use the chain rule here. So it's negative sine of 2x times the derivative of the inside, which is 2, and then times dx. Okay, so I can see that I have sine 2x dx, and I have that in here as well. So I'm going to solve for that, which means that negative 1 over 2 du is going to be sine of 2x dx. Okay, and now I know how to substitute. So this cos of 2x is my u, and sine 2x dx I'm going to replace with negative 1/2 du. So my integral is going to become 1 over u times negative 1/2 du. So I can pull out the negative 1/2, and then I have 1 over u du, which we've had a couple of times already. So hopefully we know that that's ln absolute value u plus c is the antiderivative. And now I can plug in my u. So this is negative 1/2 ln absolute value of cos of 2x plus c. So that is my indefinite integral here. So some of the trig functions have easy antiderivatives because they match sort of the derivatives. Tan is not the derivative of any of the trig functions. It's within the derivative of some, maybe, but it's not an actual derivative. Okay, so it turns out that to get the derivative of tan of 2x, I actually need to take, or to get the derivative to be tan of 2x, I actually need to take my function to be a ln of a cosine. Okay, now maybe because this one is so weird, let's just check. Okay, so we can check for all of them, but I'm going to check for this one. So if I take negative 1/2 ln absolute value cos of 2x, okay, but the plus c, the derivative is going to be 0, so I'm just going to leave that out. So the negative 1/2 can come out. Now I want to differentiate ln of cosine. The absolute values for the derivative don't mean anything. Okay, so that's going to be, when I take the derivative of ln, it's a 1 over the thing inside. Okay, and then I want to times by the derivative of the thing inside. Okay, which we just did actually. So this is negative 1/2 times 1 over cos of 2x. And then this is going to be negative sine of 2x times 2. Okay, so I see the 2's cancel out. The negatives cancel out. So I get sine of 2x over cos of 2x left over, which is actually tan of 2x, which is what I started with. So I know that I got the correct antiderivative. Okay, one more. This one's a little bit trickier, but it looks similar to one we've done already. So the substitution isn't the tricky part. Okay, so so you probably think that we should let u be 1 minus x, the thing inside the square root. So that means that du is equal to negative 1 times negative 1 times dx, so the derivative of the thing above, times dx. So I know that I know that this part in here is going to be my u. Okay, I can solve for dx, so negative du is going to be dx. Okay, so this part is that. But now the question is, what about this? Okay, we don't know how to replace that one. So what we're going to do is actually rearrange our substitution. So I see that there is an x here. Okay, so just like I rearranged this equation to solve for the thing that I want to replace, I can do the same thing here as well. So if I solve for x, x is actually 1 minus u. So now I know how to replace x. Okay, so that's actually going to be my 1 minus u. So that means my integral x square root 1 minus x dx is going to be 1 minus u times square root of u, or u to the 1/2, times negative du. Okay, so if I expand this out, so I can bring, so why is this, the reason that the u version is better than the x version? Because you might be wondering, it looks very similar. The problem is the square root. So with the square root there, I can't bring the x through. So that I can't simplify. Whereas with the u's, because the thing with the subtraction now has exponent 1, I am able to expand in. Okay, so that's what makes this version better. So that's going to be the integral. So I'm going to bring the negative through as well. So it's going to be positive u to the 3/2 minus u to the 1/2, and then du. Okay, so that's bringing the negative through as well as the u to the 1/2. So imagine taking, maybe I'll just write that here. So we take negative u to the 1/2. That's what's actually going in. So you should get that. So now I can take the antiderivative of this. So using the power rule, so if I add 1 to 3/2, I get 5 over 2. So that means I'm going to have a 2/5 out front. And if I add 1 to 3 over 2, or sorry, 1 over 2, I'm going to get 3 over 2. So I'm going to have a 2/3 out front, and then plus my constant. And now I just have to replace it with x's. So u was 1 minus x, so it's going to be 2/5, 1 minus x to the 5/2, minus 2/3, 1 minus x to the 3/2, plus c. So here is my indefinite integral. And again, if you take the derivative of this, you should get that. Okay, so x times square root of 1 minus x. So it's not obvious. I recommend that you check. Actually, maybe I'll just check right now for you. Why not? Okay, so if we check, we want the derivative 2 over 5, 1 minus x to the 5 over 2, minus 2/3, 1 minus x to the 3 over 2. The c is going to go away, so again, I just left it. So this is 2/5 times, so I bring the 5 over 2 down, and then I have 1 minus x to the 3 over 2, and then I have to times by the derivative of the inside, which is minus 1. And then I have minus 2/3 times, bring the 3 over 2 down, and I have 1 minus x to the 1 over 2, and again times the derivative of the inside, which is minus 1. Okay, so the 2's and the 5's, those cancel out. Same here, those cancel out. So I just get negative 1 minus x to the 3 over 2. And here I'm going to have plus 1 minus x to the 1 over 2. So I can pull out 1 minus x to the 1 over 2 to the smaller power. And I'm going to have negative 1 more, so to the power 1. And here I just have a 1 left over. I'm going to have if I bring this negative through, I'm going to have negative 1 plus 1 is going to go away. So I'm just going to have 1 minus x to the 1/2, so square root of 1 minus x times x. Okay, and that is exactly what the integrand looks like, but with a 1/2 exponent instead of the square root. Okay, so we do have, in fact, an antiderivative of our integrand. So that's using the method of substitution. Now be careful when you're using this. You want to try to think about whether or not you can simplify before you just blindly start to use substitution. Or if you just know the antiderivative right away, then you don't need substitution as well.